Hi, in this video I'd like to talk a little bit about the diagonalization theorem and kind of the idea behind it. So the theorem is a very useful one, especially when modeling with dynamical systems where there are state transitions. And the first part of the theorem we'll write this way. We'll say that an n by n matrix A is considered to be diagonalizable. That's a word we're going to use. If and only if A has n linearly independent eigenvectors. In fact, A can be decomposed. This is called a decomposition because we are taking A and we're decomposing it into a product of separate matrices. And you might think at first this is a bad idea because we're creating more work out of something that was, in fact, not a lot of work to begin with, but it has some very nice features. So it turns out that that D, the matrix D, is a diagonal matrix that contains the eigenvalues. So D looks like this. Let's just say that we have a 2 by 2 system. This would be lambda 1, 0, lambda 2, 0. So it would be a diagonal matrix. It would have the eigenvalues along the diagonals. The useful feature that this has is that if you exponentiate, let's say D squared, it turns out, and you can show that this will happen, for only diagonal matrices, you will end up with the square of the diagonal entries along the matrix. So it's really easy to exponentiate a diagonal matrix. It ends up just being the exponentiated diagonal components. So if and only if this is possible, that if the columns of X are n linearly independent eigenvectors of A. So they have to be linearly independent eigenvectors of A in order for this to work. In this case, the diagonal entries of D are eigenvalues of A that correspond respectively to the eigenvectors in X. And then X inverse, of course, this has to be, X has to be, consist of n linearly independent eigenvectors because otherwise X would not be invertible. So let's kind of prove this theorem. Let's start with an interesting notion here. So one thing that we know is that for a system that has eigenvalues, it will satisfy the equation AX equals lambda X. Okay, so if I have, we'll just kind of prove this sort of, we'll call this sort of a semi-proof because we'll only prove this for the 2 by 2 case. Suppose A is 2 by 2. Okay, so that means that I have two eigenvectors. Sorry, I wanted to use V's here instead of X's just to indicate that they're eigenvectors. So I know that AV1 will produce a lambda 1 multiple of V1. And I also know that AV2 will produce a lambda multiple of V2. Okay, so what I can do is if I put these things together and I create sort of a pseudo matrix out of these things, so I'll write AV1 and AV2 as elements of a matrix. Okay, so basically these are columns because AV1 will produce a multiple of lambda V1. So I'll kind of use these little arrows to indicate that this is a column vector and this is a column vector as well. And then what I can do over here is I can also do something similar. I'll equate the components. AV1 is equal to lambda V1 and AV2 is equal to, lambda 1 V1, and this is equal to lambda 2 V2. So again, these will be column vectors because I can only equate vectors to vectors. So one thing that I'm going to do here is I am going to argue that this will be the same thing as me taking a matrix that contains lambda 1, 0, 0, lambda 2, and multiplying that by a matrix that contains the eigenvectors V1 and V2. Okay, so it'll look like this. There'll be two eigenvectors side by side. Don't need that part there. So these move up and down, of course. These are vectors. And so if I multiply V1 times the first row, I will end up with lambda 1 V1. And then lambda 2 V2 will strike down here when I multiply by the second column. So we end up with essentially a matrix that we're going to call D. That's going to be the diagonal entries are the eigenvalues. And this is the matrix X. And I'm going to do a similar thing here. I'm going to write this as A, the matrix A, times the matrix that contains V1 and V2. Okay, so normally what this would mean is V1 would multiply by the A matrix and V2 would multiply by the A matrix. So really think about this as a matrix multiplied by another matrix. And so this again is the eigenvector matrix, and I'm going to call that X. So this is AX equals DX, and provided that X is invertible, if x is invertible, so this is the assumption that was stated earlier, that these have to be linearly independent eigenvectors, and if that's the case, then I can further reduce this product, as I can isolate this in terms of A and right multiply by x inverse to cancel out the x, and right multiply by x inverse here to excuse me, I'm doing this the opposite way. Let's see. I take this back. So what I actually wanted to write was these in reverse order. So let me flip these around. I won't write that, but what that will end up giving me is xd, not dx. So let me do a little bit of erasing here. Okay, let's try that again. So this will actually, and the product will make more sense this way as well. We'll have v1, v2, and then to keep our dimensions the same, we have 2 columns in here. Therefore, we would need 2 rows in this matrix. This makes more sense now. So lambda 1 would, and 0 would be lambda 1 times v1 plus 0 times v2, which is simply lambda v1. And then in the next column, it would be the product of this and this column here, which would be 0 v1 plus lambda 2 v2, which gives me the second column in this matrix. So this is ax equals x times d. And as long as x is invertible, I can now solve for matrix A. I mean, I already know what's in it, but I can express A in terms of all the other components. And now I'll right multiply by x inverse, and I'll right multiply by x inverse over here as well. That becomes the identity. I have AI equals x dx inverse, or A equals x dx inverse. This is a useful theorem because this decomposition allows me to exponentiate a matrix that to a very large power. This would be a lot of computing power if you needed to do this with some piece of software. If A were tremendously large and the power was tremendously large, then doing the operation would be extremely complicated. However, computing eigenvectors can be done, and computing the inverse of an eigenvector matrix can be done. And I'm going to argue that exponentiating the A matrix reduces down to only having to exponentiate the diagonal matrix. So let's see how this works. So A squared is equal to A times A. And again, the reason this is useful is because of the complexity or the amount of computation. It could really bog down a computer. So I know that A is equal to x dx inverse. That's the first A. The second A is also equal to x dx inverse. And matrix multiplication is associative, so I can write this all out as one big product. And what I notice happens here in the center is I have x inverse times x, which is equal to the identity. So that basically reduces that to the identity, leaving me with xd dx inverse all multiplied together. Well, d times d is d squared, and I get xd squared x inverse, and that's equivalent to a squared. A cubed would be a similar process, except we'd multiply by another factor of x dx inverse, and the xd, let's kind of put it off to the side here, this x inverse and this x would cancel out, produce the identity, and I'd have xd dx inverse, which would boil down to this computation here. Okay, so that is one of the useful features of that matrix. Part 2 of this theorem is the one that we like to use for dynamical systems. If A is a diagonalizable matrix, in other words, it has n linearly independent eigenvectors, and is a state transition matrix, in other words, A is a matrix that when I multiply it by a current state, I get the next state, then we've argued that I can actually write a function that's almost as close to a scalar function as I can get to figure out the teeth state. I can basically, it boils down to exponentiating the eigenvalues. Well, if you see the connection here, these are very similar ideas that we're getting from this state, where d squared will just be the square of the eigenvalues. So they're very linked. That's why I'm calling this part 2. And it breaks down like this. Let's actually kind of create a little proof for this. So we'll just assume, again, A is 2 by 2 to keep this simple. Now, if my initial state, x naught, as long as the eigenvectors v1 and v2 are linearly independent, what this allows me to do is that means I can create any vector in the space that V1 and V2 span, which if A is 2 by 2, that means these guys are 2 by 1 and 2 by 1. And my state vector is a 2 by 1. So that means what I can do here is I can express the initial state vector mathematically as a linear combination of the two eigenvectors. Because they're linearly independent, they're in the same space, that means any vector in that 2 by 1 space can be created by those two eigenvectors. This is where things become really neat, because to get the x1 state, recall that that was taking the 0 state and multiplying it by the state transition matrix A. Okay, so that's going to be taking A, I don't know why this is spiking, times x naught. But what I know is that x naught can be expressed as a linear combination of the eigenvectors. So I'll write it like this, plus k2 v2. And if I do a little bit of operation here, this is just a scalar, so I can move the matrix past the scalar, distribute it past the scalar, distribute it past the scalar there. I get k1a v1 plus k2a v2. And if I look at this carefully, I see that right there, that is part of the eigenequation. That's the left-hand side of the eigenequation. And I know that a v1 is equal to lambda 1 v1. So I'm going to do that and write this as lambda 1 v1 plus k2 times lambda 2 v2. And that is how I can write the x1 state based on just knowing the eigenvectors and the lambdas. x2 state is not much different. That's equal to a times x1. So x1 I know it can be expressed in terms of all of this stuff, k1 lambda 1 v1 plus k2 lambda 2 v2. And if I distribute this again, same kind of principle, except k1 and lambda 1 are both scalars, so I can pass those forward beyond the two scalars and write k1 lambda 1 a v1 plus k2 lambda 2 a v2. And again, I'm going to make the same substitution here. Those are equal to lambda 1 v1 and lambda 2 v2 respectively, so I get k1 lambda 1 v1 plus k2 lambda 2 v2. So this is all a mathematical principle of doing this, and lambda 1 is a scalar, so lambda 1 times lambda 1 is lambda 1 squared, lambda 2 times lambda 2 is lambda 2 squared, and so lies my formula that I can take the previous state and multiply it by a to get the next state. And it appears that the pattern is that if I want to find the kth state, I would just need to take lambda to the k power, lambda to the k power, which leads me back to this diagonalization. And so that's where that comes from. And the reason I thought this would be valuable is because we often talk about these theorems and where do they come from. So it helps to kind of put things together and put some of the algebra together with some of the logic behind matrices, and this is where that comes from. So hopefully this video has been helpful, and that's where the diagonalization theorem comes from.